Welcome to our exploration of classical mechanics. Today, we'll compare three fundamental approaches to mechanics: Newtonian, Lagrangian, and Hamiltonian mechanics. Each of these frameworks describes the same physical phenomena, but with different mathematical tools and perspectives. Let's dive in and understand their similarities and differences. Let's start with Newtonian mechanics, the most intuitive approach, and probably the one you're most familiar with. Newtonian mechanics is based on Newton's laws of motion, particularly the second law, which states that force equals mass times acceleration, or F equals ma. Newton's approach uses vector equations to describe motion and deals directly with forces acting on masses. When we use Newtonian mechanics, we identify all forces acting on an object, apply F equals ma, and solve for the resulting motion. Let's consider a simple example to illustrate Newtonian mechanics: a ball rolling down an incline. We have a ball on a frictionless incline at angle theta. The forces acting on the ball are its weight mg pointing downward and the normal force n perpendicular to the incline. We can decompose the weight into components parallel and perpendicular to the incline. The parallel component mg sine theta causes the ball to accelerate down the incline, while the perpendicular component mg cosine theta is balanced by the normal force. Using F equals ma along the incline, we get mg sine theta equals ma simplifying equals g sine theta. So the ball accelerates down the incline with a magnitude of g sine theta independent of its mass. For a 30-degree incline, the acceleration would be approximately 4.9 meters per second squared. Now, let's move to Lagrangian mechanics, which offers a more elegant and powerful approach to classical mechanics. Instead of dealing directly with forces, Lagrangian mechanics is based on the principle of least action. It introduces the Lagrangian function, L, which is defined as the kinetic energy T minus the potential energy V. One of the key advantages of Lagrangian mechanics is that it can use any set of generalized coordinates, not just the standard Cartesian coordinates. It employs the Euler-Lagrange equations, which state that for each generalized coordinate q sub I, the time derivative of the partial derivative of L with respect to q dot sub I minus the partial derivative of L with respect to q sub I equals 0. Let's solve the same problem of a ball rolling down an incline, but now using Lagrangian mechanics. First, we choose our generalized coordinate. Since the motion is constrained to be along the incline, we'll use the distance s along the incline from the starting point. The kinetic energy is T equals 1/2 mv squared, or 1/2 m s dot squared, where s dot is the time derivative of s. The potential energy is V equals mgh, where h is the height. Since s and h are related by h equals s sine theta, we have V equals mg times s sine theta. Now we can form the Lagrangian. L equals T minus VL equals 1/2 m s dot squared minus mgs sine theta. Applying the Euler-Lagrange equation, the partial derivative of L with respect to s dot is m s dot. Its time derivative is m s double dot. The partial derivative of L with respect to s is negative mg sine theta. Setting these equal, we get m s double dot plus mg sine theta equals 0 s double dot equals negative g sine theta. So the acceleration is g sine theta, the same result we got with Newtonian mechanics. Finally, let's explore Hamiltonian mechanics, which builds on Lagrangian mechanics, but takes a different perspective. While Lagrangian mechanics uses the Lagrangian L equals T minus V, Hamiltonian mechanics is based on the Hamiltonian function h, which represents the total energy of the system. H equals T plus V. The key variables in Hamiltonian mechanics are the generalized coordinates q sub I and their conjugate momenta p sub I. These form what we call the phase space, a powerful mathematical construct that's central to Hamiltonian mechanics. Instead of the second-order Euler-Lagrange equations, Hamiltonian mechanics uses Hamilton's equations, which are first-order differential equations. Q dot sub I equals partial h partial p sub I, p dot sub I equals negative partial h partial q sub I. Hamiltonian mechanics provides a natural bridge to quantum mechanics and statistical mechanics, making it invaluable for advanced physics. Let's solve our incline problem once more, now using Hamiltonian mechanics. As in the Lagrangian approach, we use s as our generalized coordinate, but now we need the conjugate momentum p, defined as p equals partial L partial s dot, which is m s dot. The Hamiltonian is given by h equals p s dot minus LH equals p s dot minus 1/2 m s dot squared minus mgs sine theta. Substituting p equals ms dot, we get s dot equals p divided by m, and the Hamiltonian becomes h equals p times p over m minus 1/2 p squared over m plus mgs sine theta, simplifying. H equals p squared over 2m plus mgs sine theta. Now, we apply Hamilton's equations. S dot equals partial h partial p, which is p over m. P dot equals negative partial h partial s, which is negative mg sine theta, taking the time derivative of the first equation and substituting the second. S double dot equals p dot over m equals negative g sine theta. And once again, we arrive at the same answer. Now that we've seen all three approaches, let's compare them side by side. First, let's look at their main focus. Newtonian mechanics focuses on forces and acceleration. Lagrangian mechanics focuses on energies, kinetic and potential. Hamiltonian mechanics focuses on total energy and phase space. Next, the variables they use. Newtonian, positions and velocities. Lagrangian, generalized coordinates and velocities. Hamiltonian, generalized coordinates and momenta, the form of their governing equations. Newtonian, F equals ma, second order. Lagrangian, Euler-Lagrange equations, second order. Hamiltonian, Hamilton's equations, first order. And finally, their strengths. Newtonian, intuitive and direct for simple force problems. Lagrangian, handles complex constraints and field theories. Hamiltonian, excels in advanced topics and connects to quantum mechanics. In conclusion, all three formulations, Newtonian, Lagrangian, and Hamiltonian mechanics, describe the same physical phenomena and give the same predictions about motion, as we saw with our incline example. However, they approach the problem from different mathematical perspectives, which makes each formulation better suited for certain types of problems. The evolution from Newtonian to Lagrangian to Hamiltonian mechanics represents a progression toward more abstract and powerful mathematical frameworks. This progression has enabled physicists to tackle increasingly complex problems and has led to breakthroughs in our understanding of both classical and quantum physics. Thank you for joining us on this journey through the three formulations of classical mechanics.